Hello, today I hope to pop together a few of these ring lights, test them, make sure they're okay, fault find, and of course make them work. I've referred to them in a previous mailbag. Today though, the stencils arrived, I've got my circuit diagram, and I'm just going to pop them together. Later on in the video I'll also look at the circuit diagram and just talk about the design choices that I made.
These are LED ring lights, 12 LEDs, and a couple of things of interest. So the first is they're on aluminium board. This is the first aluminium board I've made. That was quite an interesting process in its own right, and this is single-sided, which is also quite rare for me. Part of the reason for that is that JLC PCB, who made this, only do single-sided aluminium. You can get some manufacturers doing double-sided aluminium, but you know, the normal thing with that is you've got through holes, vias and things like that, and they have to be dealt with differently on aluminium because of course it conducts, so they have to sort of put some additional manufacturing steps in. So this is the stencil, and as you can see it's stainless steel, quite a large stainless steel sheet, and yeah, obviously here is the cutout section in the middle. It's coated with plastic for our protection. Lovely. So that looks all right, no problem with that at all. To be honest, I had quite a lot of stencils made by JLC PCB and they've all been absolutely fine. The downside with them is the shipping cost. So without the stencil, these PCBs are essentially, they cost virtually nothing, including shipping, as long as you don't want it next day or something silly. But once you put the stencil in, all of a sudden the weight is through the roof. And so is the postage cost. Okay, there we go. So white aluminium board with a hole cut in the middle. And so we've got all the diodes marked. Over here we've got a space for an op amp, and there's a MOSFET space down here, and most of it's just LEDs. Okay, so let's have a go at doing some assembly. For today, we'll try the overhead camera, see if we can get away with it. Let's turn it up down so I can kind of see what I'm doing. That way it'll probably be best, I think. And I'm just going to paste this to begin with. So I'm using this paste here. So the advantage of this one is refrigeration not required and a long shelf life. Okay, let's try and get this the right way around then. Do you think it's that way? I hope it's that way. So I reckon that's about it. I just put my elbow down on the little piece of wrapper. Let's take a quick look at that and make sure it's all pasted. How about you? I'm having difficulty seeing that marking if it's there. Yeah, I think that corner just there is missing. If that's the case, I might have to switch to using a microscope to do this, because that is really, really small. So I'm actually going to turn the board upside down because it'll be easy for me to do the placements. The marking on the LED is so tiny that I've just resorted to using a small power supply just to check which way round each one goes before I place it. It's by far the fastest. Now again, since this actually is running on an analogue circuit and that capacitor there is really for pulse width modulation just to help smooth things, it's not actually that much value to me. I could have just left it off, but just for completeness, there it is. we are ready to reflow that. So I'm going to go and do that now. Okay, so in terms of soldering, as far as I can see, all these solder joints are good. This will be the control voltage. So this can be controlled by a pot, and there's an extra plus and minus just in case we need to take those out to the pot from the board, but I don't need to for my purpose. And an input wire which has the controlling voltage on it, and that can come from an ADC or a pot, or it can be a pulse width modulated signal, whatever you fancy really. Now I'm conscious that this board will tend to soak up heat, so I am going to just, although I did the solder stencil does tin these connections, I am nevertheless going to actually add some additional tinning to them manually now, and this is just so that we've got some heat in the board before I apply the actual wire to the pad. And obviously I have tinned the pad quite heavily and the wire quite heavily as well. So these are my 3 leads, and I will just pop that through that hole. So in terms of mounting, this has 3 screw holes for mounting and 1 hole that's larger near the edge for feeding any cables through to the other side of the board, just in case you need to do that. So this actually fits inside a recess in my pick and place bed, and so there's no place around the edge to feed the cable, and obviously the camera is sticking through the middle. So it's not the neatest job I've ever done, but it will do for me for today, I think. Right, time to plug it into something and test it. Okay, and as usual in these cases it doesn't work. Okay, let's have a toggle around at a few voltages and make sure everything's where it should be. So first up, let's test our input voltage. There's our 12 volts in, that's good news. Okay, before we press on with the fault finding, I just want to take a look at the circuit diagram, understand how this circuit works, because that will be important as we try and fault find. The circuit is a linear circuit. I decided just to go away from the normal pulse width modulation for a change, and I just want to put this on a pick and place bed and have a pot on the front to change the brightness. And yeah, I could do that with a timer circuit and pulse width modulation and stuff, but I just wanted a really simple circuit, all the circuit on the actual ring light itself, and yeah, job done. So here we go. Anyway, there would be benefits for a pulse width modulation circuit, but in terms of power dissipation and stuff, but you know, this will be absolutely fine. I should qualify this, I've made this a bit general purpose. I'm going to use it as lights in a few other places and things like that as well, and I might also run it off battery power. So yeah, there's some choices made there, but the components chosen on the simulation that we're looking at the moment are the values chosen for the resistors in particular are for a 12 volt supply running as a ring light on my pick and place machine. If I were to run it at different voltages, then I would choose different component values potentially. If I were to run it in battery, then I might alter the spread of the power dissipation and stuff like that. But you know, for the moment, I've got it for this particular purpose. Let's look at the 2 sections of the diagram then. So the first section are the LEDs. These are 3.2 volt forward voltage drop white LEDs, and they're 20 milliamps each, thereabouts. And yeah, this circuit will work. It doesn't care whether these are 2 volts, 3.2 volts, 3 volts. The way this circuit works is to regulate the amount of current flowing through these LEDs to regulate the voltage, to regulate the brightness. The voltage across each LED will then follow the current. We've got some resistors down here. The primary reason for these resistors is actually to spread out some of the heat dissipation across the board, because each string of series LEDs drops 9.6 volts, and I'm running a 12 volt supply. So yeah, there's 2.4 volts kicking around somewhere that needs to be dealt with,
and in total, since I've got 4 strings of LEDs, that's 2.4 volts at 80 milliamps floating around, that has to be dissipated as heat, and that's going to be dissipated in these resistors across resistor 6 through resistor 9, in this MOSFET just here, and in this resistor down here, because that is the line of current flow through the diodes. So they go through the diodes, through the MOSFET, which regulates the current, and it regulates the current because essentially when it's fully on, it's got a very low resistance, about 1.5 ohms. When it's fully off, it's got a very, very high resistance up in the hundreds of mega ohms. And resistor 4 is there actually, so there's a single resistor that has all of the current passing through it, and we use that resistor to sense the amount of current, and that passes through back into this op amp to control everything. So let's have a look at that second part of the circuit just here. So I said that at maximum brightness, these LEDs will be passing in total for the whole lot 80 milliamps. Now if we look at this resistor 4, that means that has 80 milliamps flowing through it, because that is a single point through which all that current flows. So 22 ohms, 80 milliamps is 1.76 volt drop across that resistor. The bottom of the resistor is joined to ground, so the top of the resistor is at 1.76 volts. Simple. That 1.76 volts gets fed back to the op amp. Okay, on our input can sweep in this instance between 0 and 12 volts, and the reason is that in the pick and place machine I will just have a pot across the 12 volt rail, and it will pick off some voltage between 0 and 12 volts and put it on the V in section of this circuit. It then goes into this voltage divider here, and the output going into the positive part of the op amp is at 12 volts will be 1.78 volts. Now 1.78 volts, 1.76 volts, using preferred values of resistors, which will be 5% resistors. Those are essentially the same value with the tolerance of resistors. So if our current flowing through the diodes and the MOSFET is a little bit low, then the voltage across resistor 4 will be below 1.76 volts. So let's say it's going to be a volt. So I've got a set point coming in on my op amp of 1.76, 1.78 volts, thereabouts, and 1 volts on the negative. That will cause the output of the op amp to swing up towards the 12 volts. That's turning on this MOSFET more, allowing more current to flow through it, and therefore more current flows through the LEDs and more current flows through resistor 4. The voltage across resistor 4 rises. And that adjustment to the output voltage of the op amp and the feedback from resistor 4 will essentially ensure that the top end of resistor 4 is always the same voltage that we have selected on our input up here after the voltage divider, of course. So essentially we're setting a voltage on the input of the op amp, and the op amp and the MOSFET between them are ensuring that that voltage appears on the top end of resistor 4, which means that we can vary the current flowing through resistor 4 between 0 and 80 milliamps. Okay, so that's the actual mechanism. It does have a small flaw, and that is that this is a really cheap op amp. It's an LM358, and it can't actually go all the way down to ground. So this is a single side supply, and unfortunately I haven't made any adjustments to this to allow this line here, the output from the op amp going into the gate of the MOSFET, to go down all the way to ground. This MOSFET has quite a low gate voltage, so the end result of that is even with 0 volts on the input, we're probably going to have a little bit of current flowing through the MOSFET, and therefore a little bit of current through these LEDs, and they might just light dimly when we've set 0. So instead of going from completely off to ultra bright, they will go from very, very faint to ultra bright. Now we could alter the circuit a little bit. We could put some diodes in to create a little voltage step so that we can achieve what appears to be a 0 volts on there. We could just put a diode in it to create a voltage drop on the output from the op amp to the MOSFET. If we did that, however, we wouldn't be able to pull the voltage down very effectively. Turning to dimmer would be harder, and that's because essentially the gate on this MOSFET is a bit capacitive, and therefore if I have a diode which only allows current to flow towards the MOSFET, how does my MOSFET gate discharge? Well, I would therefore need a bleed resistor going down from the MOSFET gate to ground to help that MOSFET reduce its conductance when I wanted it to do so. Otherwise the op amp and the MOSFET wouldn't regulate quite right. So yeah, we could put a voltage drop diode in there if we wanted to, and we could also put some diodes in the power circuit so that in actual fact the output appears to the MOSFET and this resistor to be able to go all the way down to ground, but it just complicates the circuit a lot more than it needs to be. And I just want to, and this needs to fit onto a 42mm round aluminium board, single-sided, with a hole cut in the middle, and there's not a lot of space to put stuff, and yeah, it's easier just to leave it like this. If I want to turn it off fully, I can just put a switch in the power supply line. It's very simple. A quick look at the graphs then. On the left hand side we've got the simulation running. Top graph is the inputs, and we've got a 12 volt supply showing, and we've got a stepped, red is the stepped input voltage. Corresponding on the graph below we've got this green section here, which is the amount of current flowing through the LEDs. Now please bear in mind that we're starting this simulation at 0, so at that point the capacitors aren't charged, the smoothing capacitor across the op amp isn't charged, nothing's happened to the MOSFET so far. It's kind of at a nothing state, and that isn't really very realistic once the circuit starts operating. So it's kind of not quite as true as it should be at the very start, but I don't really care, it's fine. The purple line is the power dissipation in the actual MOSFET. So we can see though the key thing is that as the voltage increases, the green line, which is the current through one LED, diode 1, increases and regulates exactly in step with the voltage on the input, and that's it. That's how the whole of this circuit works. If we want to run it on a different voltage, we can do, but we'd need to just think about the values used for these resistors here and this resistor down here. This resistor in fact is a bit critical because it's got all the current flowing through it, so it would be sensible to reduce that to, let's say, 10 ohms, something like that. That would give us a lot of headroom for power in that specific resistor. It's an 805 resistor, so you can handle a fair bit, but not limitless. And it is of course on an aluminium board, so it dissipates heat very effectively. The MOSFET can handle up to 370 milliwatts, but if you put this up to 24 volts, then you've got kind of, I don't know what you've got, 1.5 watts or something like that to dissipate. That's a huge amount. This isn't really designed to go up to 24 volts. If we reduce our voltage down to, let's say, 9 volts, then we won't be able to get our full 80 milliamps through these, because there's just too much forward voltage drop across these diodes. But essentially this is quite a useful little circuit in its own right, ignore the LEDs, in so much as what we've got here is roughly a 200 milliamp capable, if we reduce this down to 10 ohms, a 200 milliamp capable regulated current supply, or current sink probably would be better since it's on the bottom, not the top. But yeah, there we go. Anyway, let's go back and see what's wrong with it. So C2, 5 volts at one end, 12 volts at the other, I hope, 12 at the other, yeah. So resistor 4, 0.8 volts at one end, 0.8 volts at the other end. Well, that isn't right, is it? Pin 4, which should be ground, is not grounded. Yeah, that is not right. .20 meg. So that is open circuit to ground. Okay. Well, it looks to me like that pin on here is correctly connected. In fact, the soldering on there looks great, I think. Is there a fault on the circuit board then? Yes, there is. There's a fault on the PCB, which is really surprising because this passed its checks. So I really do need to look at that. But pin 4 is not connected to anything other than these two resistors, and they are not connected to anything else. So we need a mod wire on that. Okay, right, let's give it another go. So I'm interested that it's driving at that. I mean, these do look quite bright on the camera, but they are actually pretty faint. They're just like panel indicator light brightness, not really illuminating as such. Turn the brightness up, very, very quickly picking up brightness at the bottom end. So that's 0.4 volts. 1.3 volts, 2.3, and seriously I don't really get any brighter than that, and that is quite a lot of illumination. You can kind of see it illuminating the inside of my hand here. That implies another fault, because I should get full 12 volts, nice, easy to control, and I'm not. So what could be causing that? Looking at the diagram. So obviously there could be a problem with the feedback circuit, but let's leave that aside for the time and just think about the voltage divider. Because if resistor 2 isn't grounded, for example, then this voltage divider won't be working properly. So let's measure the voltages as usual. If I can kind of see past the glare, I'm just going to turn this down a bit. So that's 1.74 volts coming in. Find the ground connection, which is just here, and I'll find the in, and then we've got the input resistor, and then we go into pin 3. Not in ohms, that would be better in voltages, of course. Yeah, look at that, 1.66. Measure the input voltage, 1.72. So not dropping anything on that resistor 2, and resistor 2 is the same voltage on both ends. So resistor 2 is this guy going down to ground just here. So my suspicion is I've got a bad solder joint on that. We'll have a look. That should be that should be connected. It doesn't matter how many times I resolder this bloody resistor, that ain't gonna work. Interesting. Is it just this board or is it all of them? Because I'm kind of looking at the diagram just here with all the connections on and things like that, and I know you can't see that because the zoom's wrong, but yeah, there's the diagram and it shows that it's connected. It's getting an unpopulated board, and I can see the trace. I mean, I can actually see it underneath the white. It's right there. And there is no electrical connection. You've got to be kidding me. So here's the IC. Oh, look at that. Look at that. That track does not run into the middle of the pad. It ends there. You can see the round end on it. Piss. So when that's been etched, it's actually pulled back.
Unbelievable. Oh, I can't believe that I did that. And I can't believe that this passed the pissing test. I really do need to look at that test result and find out why this thing, despite the fact it's faulty as hell, passed its design rule checks. Well, I need a new resistor because I've lost that one, 82k. Okay, what should hopefully be the final test now. So, quick look at the diagram. So here's the IC. This is the op amp that is the comparator essentially for the current set. And this is pin 4 of it down here. And these connections here should all be going up to ground. So there's actually a track missing. So anyway, I'll put a bodge wire in for that. Now the next problem here is this one that's labelled resistor 1, which is actually resistor 2. So I don't know quite what's happened to the label for that. I suspect it's as I've moved things to the left to keep them away from this hole. I suspect I've lost something. But anyway, this is resistor 2, this is resistor 1 up here, this is resistor 2 down here. And the bottom of it appears to be connected up to ground as well onto pin 4. But in actual fact, looking at the geometry of that track actually terminates exactly on the boundary of resistor 2 and not in the middle of its pad. It's very important these tracks run to the centre of the pad so they hang around when we move things around. And so although it's not visible on here, then a bodge wire has to go in there to sort that as well. So that's kind of pretty annoying, but not the end of the world. And the good news is I can fix all of that without having to remove anything on the board, which means I don't have to have a new stencil made. So I can get these for, you know, £5 or something like that, the whole lot just remade. So that's all right. Anyway, here's the board. So it's powered up. I've got 12.44 volts input voltage. So this is intended to be able to power off a battery, for example. So I should be able to take down to about 10 volts or up to about 13.5, 14 volts, something like that, with no problem. Of course, on the actual pick and place machine, it'll be running off a 12 volt regulated supply, so that's all right. But yeah, I just wanted a bit more versatility, so it should be able to work at various voltages. Anyway, 12.44 is set at the moment. The input is essentially turned off. And although these LEDs look to be on, they are on very slightly. You wouldn't even be happy if these were indicator lights on a panel or something like that. They're too faint. You would be annoyed. The exposure is exposing this board quite nicely, I hope, and it's fixed so we can see these lights adjusting, because otherwise the lights would always stay at the same brightness once they get to a certain brightness and everything else would darken down. You wouldn't be able to see what's going on. So let's turn it up to 1 volt. So I'm expecting about 10 volts to be about my maximum. It might overdrive a fraction, but we'll see. So let's turn it up to 1 volt on the 1.1 volt. Let's try and get 1 volt. So there we go, 1 volt on the input. Now these are about bright enough now for a display panel or something like that. They're not really bright enough for illumination. I mean, they'll illuminate a few inches. You could perhaps, you won't be able to read by it at night or anything like that, for example. Okay, let's see. And we're drawing barely 10 milliamps. Let's just turn our input up then. Gradually, 3 volts now. 5 volts, we're drawing 30, 40 milliamps, somewhere between 30 and 40 milliamps. 7 volts, 50 milliamps. 8 volts, 60, 70 milliamps at 10 volts. And there we go, 11.338 volts, and we've got the 80 milliamps, which is the kind of theoretical brightness. And this is pretty bright. Now you can kind of see the brightness on my hand, and this is about as bright as I do want it for the purposes of my pick and place machine. Let's put a piece of paper next to it. We should be able to hopefully kind of see how bright that is. So it's only illuminating a couple of inches on the pick and place machine, but that's pretty nice. It's bright. So yeah, pretty pleased with that. That is performing as it should do. So 12 volts, input exactly. Yeah, drawing 80 milliamps, which is what it should do. Illuminating nice and brightly. Now, if I change the supply voltage, so I'm going to turn the supply voltage up to about 14, 15 volts. There you go. I'm running it at 17 volts now. Now I'm running it at 11.3. Now below 12 it should start dimming down a little bit, simply because it's optimized to work at 12. But there we go, that's 20 volts. That's 14 volts, 13. And basically the supply voltage is not really making any difference till I drop below about 10 volts, at which point it starts dimming because it can't regulate the current anymore. So yeah, okay, cool. That is good. Let's have a feel of the MOSFET. No, the MOSFET is running cool. The board itself is lukewarm. Not too bad at all. LEDs, yeah, they're fine. I mean, it's warm, but it's not shocking.
I figured it might be a good idea just to finish up looking at the circuit board. So I've made a very tiny modification on here. So here's our resistor 2, which was causing one of our problems. So I've made sure the ground now runs fully into the center of that pad. So that's absolutely fine now, and that connects through to the ground on the IC. Now the other problem was connecting the ground on the IC to the actual ground input. So the ground input is over here. The ground on the IC is just here. And it's extremely difficult to find a route through, because I would much prefer not to move any components around. Now I can do something with the plus, get a bit of space. I could swap these pads around, so the plus 12 and the ground are the other way around. That would be fine. I could do that without having to make a new stencil, as long as I put the pads in the same place, well, you know, in corresponding places. So that would enable me to kind of clear some of the clutter out the way, but then I would need to move this resistor here and a couple of the others, and truthfully it's extremely hard to find a mechanism by which all the components can stay in exactly the same place, so the stencil doesn't need changing, but we can get the connection between pin 5 here, which is supposed to be ground, and pin 4 here, which is also supposed to be ground. So that is really difficult. So what I've done instead is I've just popped two pads in here. These are 3 pads connected to ground here and here. So basically opposite each other on opposite sides of this IC, just so I've actually got a proper place that I can run a bodge wire round. And I think I'm just going to kind of leave it at that. Another mechanism would actually be to put a hole through both of those, and the same with some of these screw holes and things like that, and actually use the chassis to transfer the ground, but I'm not really convinced. So I'm going to go with that as a little bit of a sort of make do and mend type solution. Just the 2 exposed pads just there, so I can easily solder. Of course, a couple of idiotic mistakes on the board there. Bodge wires needed to make it work, but it does work, so that's good news, and it's a fairly versatile circuit for me. I can use it in a few different places. But I hope you enjoyed it. If you did, please, thumbs up, subscribe of course if you haven't already done so, and I'll see you next time. Bye for now.